Vibration is the mechanical oscillations of an object about an equilibrium point. The oscillations may be regular, such as the motion of a pendulum, or random, such as the movement of a tire on a gravel road. The study of effects of vibration requires measures of the overall pressure waves that are generated by vibrating equipment or structure.
If we could watch a vibrating object in slow motion, you can see movements in different directions. Any vibration has two measurable quantities: how far, which is amplitude or intensity, and how fast, which is frequency, the object moves helps determine the vibration characteristics. The terms used to describe these movements are frequency, amplitude, and period.
The figure shows our most basic example of a vibration. With no forces on it, the spring assumes its equilibrium length, A. It can be stretched, B, or compressed, C. We attach the spring to a wall on the left and to a mass on right. If we now hit the mass with the hammer, D, it oscillates as shown in the series of snapshots, D to M. If we assume that the mass slides back and forth without friction and that the motion is one-dimensional, then conservation of energy proves that the motion must be repetitive. When the block comes back to its initial position again, G, its potential energy is the same again, so it must have the same kinetic energy again. The motion is in the opposite direction. However, finally at J, it returns to its initial position with the same kinetic energy and the same direction of motion. The motion has gone through one complete cycle and will now repeat forever in the absence of friction.
The usual physics terminology for motion that repeats itself over and over is periodic motion, and the time required for one repetition is called the period. The symbol for period is letter P, letter T. It is not P because of the possible confusion with momentum, because momentum's symbol is letter P. One complete repetition of motion is called a cycle. We are used to referring to short period sound vibrations as high in pitch. And it sounds odd to have to say that high pitches have low periods. It is therefore more common to discuss the rapidity of a vibration in terms of the number of vibrations per second, a quantity called the frequency. The symbol for frequency is F. Since the period is the number of seconds per cycle and the frequency is the number of cycles per second, they are reciprocals of each other. So we can conclude that the equation for frequency is 1 over period.
Units of frequency are also commonly used to specify the speeds of computers. The idea is that all the little circuits on a computer chip are synchronized by the very fast ticks of an electronic clock, so that the circuits can all cooperate on a task without getting ahead or behind. Adding two numbers might require, say, 30 clock cycles. Microcomputers these days operate at clock frequencies of about a gigahertz.
We have discussed how to measure how fast something vibrates, but now how big the vibrations are. The general term for this is amplitude, A. The definition of amplitude depends on the system being discussed, and two people discussing the same system may not even use the same definition. In the example of the block on the end of the screen, the amplitude which is measured in distance units such as centimeter. One could work in terms of the distance traveled by the block of the extreme left to the extreme right, but it would be somewhat more common in physics to use the distance from the center to one extreme.
The former is usually referred to as the peak-to-peak amplitude, since the extremes of the motion look like mountain peaks or upside-down mountain peaks on a graph of position versus time. In other situations, we would not even use the same units for amplitude. The amplitude of a child on a swing would most conveniently be measured as an angle, not a distance, since her feet will move a greater distance than her head. The electrical vibrations in a radio receiver would be measured in electrical units such as volts or amperes.